Here I will share a little bit of my struggles of doing the SunFounders Electronics Kit Lesson 3, but not in Python, but in Rust. In this lesson we control 3 LEDs, red, green and blue, through 3 pins, 13, 14 and 15. And we control their brightness using pulse width modulation. And this is pulse width modulation, so it creates an average voltage by having a cycle, a square wave. And if you want to have a higher voltage, you have it higher for a longer time, and if you want to have a lower average voltage, you have it lower for a longer time. If it's fully high, then it's just going to be 3.3 volts, and if it's fully low, it's going to be 0 volts. Now in the Python code they have easy abstractions for LEDs, which we don't have in Rust, because pulse width modulation can be used to control not just LEDs but sound, motors and many other things. So in Python they just go, set the frequency to 1000 Hertz and set the brightness to whatever, which I don't know where that is. It's given an RGB value. Wow, it's so abstracted. In Rust we have to use the data sheet. Let's go to the code and we'll try to give a little bit of an overview. So there's a clock inside the Raspberry Pi which controls all the pulse width modulation outputs and inputs, and it clicks every 125 million times a second, so 125 megahertz, which is about 8 microseconds I think. And you can control the frequency by saying, okay, you can divide that clock by skipping every other one, so you can divide it by 2 and then you get half the frequency, and now you will get less ticks. And then you can multiply it by setting the top. So if we go here, there's the top. The top is how many times it ticks between 0 and the start of the next phase. So by default it's 65,535 times, but if you want to get a certain frequency, we're going for 1000 Hertz. Just because the Python one did it, you can set it by set a new top. So we've set our top to 25,000. So we're doing 62.5. Every 62.5 millionth of a second is a tick, because we're dividing the frequency by 2. And then we're counting 25,000 ticks to give us 1000 Hertz, 1000 cycles per second. So that phase will happen 1000 times a second. This is a lot of working stuff out, but the 3 variables important is the top is how much you're multiplying it by, the divider is how much you're dividing the clock cycle by. So divider slows it down, top slows it down as well. I don't know what I'm talking about. No, top. Yeah, top. When you decrease the top, it speeds up the frequency. Okay, so how do we? I'll just show you my code. It's nice and easy. I'm very proud of my code. So I made the state, which is what are the values of red, green and blue at any given time. I made these beautiful const functions, so you don't need to set stuff up at runtime, just at compile time. You can't use default when you're writing a const function, so I use a state black, which is down here, and everything's set to min. So it's nice and easy. Red, you just set the red to full. Yellow is green and red, and then the rest of the struct will be black. So then we have the step function, and it just steps from one state towards the next state. So if our red is lower than that red, then we'll add the step size. Saturating add means we don't overflow to 65,000, and then .min is we don't want to overflow the destination red value. Then we set up this constant state array, and it's got 8 values. It goes red, green, blue, all the different colors. Then we're setting the timer. We've already seen this. We're setting the pulse width modulation clock, how we are interpreting that signal for our usage. So the Raspberry Pi has slices, so 2 pins are hooked together, so 14 and 15. And we go here. 14 and 15 are on the same pulse width modulation slice, so they share a lot of data. They share part of the config. Where is the config? So they share the top and the divider no matter what. And then we just do this beautiful loop, and we say if our destination state is not if it's equal to this current state, then choose a new destination state. And then we take a step, and then we grab the values from the state that we just updated, red, green, and blue, and we set it to the compare. So the compare is, if we go to the board, it's how long it stays high. So if compare is 25,000, then it'll be 100% voltage, and that color will be 100% brightness. If it's 0, it'll be 0 brightness. So we set the green brightness, the blue brightness, and then we just push that to this PWM peripheral, and then we do the same for the which changes pins 14 and 15, and then we do the same for the red pin, and then we wait step duration, and here's the result. Ta-da! And it changing color. Yes, it is. So every second it'll change to a new state. That's theoretically, that's how I worked it out. I might be wrong. And thank you for watching my video. 6 minutes, not too bad.